Hello and welcome to the second class on haloalkanes. As we discussed in the last class that haloalkanes are a, an important class of compounds, aliphatic compounds, through which many other organic compounds can be prepared. That is why the study of haloalkanes are so important. And we had seen how we can prepare haloalkanes from alkanes just by the help of heat or light or both. It's a photochemical and a thermal reaction, and that too goes without saying that it is a free radical substitution mechanism. Whether you succeed with heat or with ultraviolet light or visible light or any radiation, then that will form free radicals. And also we had seen how we can prepare from alkenes, both with the help of HX, the hydrogen halide hydrohalic acids, where we have the ADE mechanism, addition electrophilic mechanism, which we have discussed in details in our class 11 program. And there is a sufficient room for carbocation rearrangement, leading to a different measured product when there is a substitution. And if you want to arrest a substitution, then you have to do something else, particularly when you are wanting a chloride. You do not go via alkenes, chloride, bromide. You can get a pinpointed haloalkane by other methods, not by adding HX, because when there is H plus ion, it will lead the mechanism in the favor of ADE, electrophilic addition. So you can't help, carbocation will rearrange. We will see today how we prepare haloalkanes by other methods. The third method that we study is the third method. This is from alcohols. From alcohols, we have again with HX. Again you are giving acid because halide ion is there. So here the order, reactivity order, and when you treat it with alcohol, as we shall study today, that OH minus is not a good leaving group. It is a very strong base, but we have H plus ion. So it will be protonated first. And then either it can go for SN1 or SN2. We shall study in details with the halide ion. In one step, if it goes, then it is SN2. So you get Rx. This I am showing SN2. SN2 only for methanol and ethanol. Others SN1. And again, there is a room for rearrangement. Just like adding HX with alkenes, here also you will have a different product like the one you, supposing this is the alcohol, isobutyl alcohol with say a HCl or HBr or whatever. Now the reaction will be driven by SN1. Carbocation has to be formed. If there is a carbocation, this is substitution. OH will go and bromine will come. So this is substitution, but since it will be going via carbocation, then we have to write SN1. So the actual product, I mean the major product will be bromide will be here. Just like we had seen in case of alkenes, there is a hydride shift. So instead of getting isobutyl bromide, you will get tert butyl bromide in presence of acid. But if there is no rearrangement, supposing it is ethanol, then, well, the mechanism, if you write in details, I have not written the mechanism in the first example. So it will be protonated, and since there is no room for any rearrangement, so there is no room for any rearrangement. So what will happen? In one step, after protonation, this is the SN2 step where the Cl minus or X minus or Br minus, say we are giving HBr, so Br minus supposing, will come here and attack from the rear side, back side, and this will go because there is no driving force for the formation of a carbocation. 1 degree carbocation is unstable, so it will favor SN2. So in one step, it will produce this plus water. You got it? So
Yes, sir.
in all other cases, you will definitely find so one of the specialized tests of alcohols to distinguish between 1 degree, 2 degree, and 3 degree alcohols is the Lucas test. Same alcohol, you have to take HCl, not HBr and HI, and take a Lewis acid zinc chloride, and you get RCl plus water. What happens in 3 degree? In 3 degree alcohol, which is most reactive, goes via SN1 mechanism. this appears as a white turbidity. The white turbidity appears within 1 minute. It is fast. Because 3 degree greater than 2 degree greater than 1 degree. So white turbidity appears in 1 minute at room temperature. You need not have to heat. If it is a 2 degree alcohol, then it is little slower. The white turbidity appears in 5 minutes at room temperature. But for 1 degree, which goes by via SN2, and inherently SN2 is slower than SN1. SN1 rate is always faster, greater than SN2. So this will not happen. No white turbidity at room temperature. Even if you wait for 1 hour and continue to sec, no white turbidity at room temperature. So this is the slowest one from which you can know. But only on heating or boiling, white precipitate appears. And the advantage of this Lucas test is at low concentration of zinc chloride, the rearrangement of carbocation is prevented. How? Because this zinc chloride, which acts as a what does acid, H plus ion is a very aggressive Lewis acid. Zinc ion, if you do not, if you take zinc ion, then zinc ion will have a bond with ZnCl2. Let me write down. Instead of showing 2 charges, let me write down ZnCl2. So this is a dative bond with the formal charge coming to this one and negative charge coming to the zinc ion. Or if it is Zn2 plus, if you write Zn2 plus, then the charge will be reduced. Plus and here plus. It is better to write ZnCl2 so that we will write H is there. H is there, 8 and 1 lone pair is there. So it is better to show a negative charge. And as a result, even if it is a 3 degree carbocation, then the X minus, for carbocation formation, this bond has to break. But this breaks in one step. So SN2 is favored here, or sometimes an intimate carbocation and this big species that are formed, which block, the SN1 process. It allows the backside to appear because this is a huge one, ZnCl2OH. So even if it goes, it breaks for 3 degree, carbocation can be formed, but it forms an intimate ion pair, and so it doesn't allow the carbocation to be active because of the attraction between the two. So you get this one with Zn, this OH goes ZnCl2 OH. So of course here Cl minus has to go because zinc has a valency 2. So it will be basic zinc chloride. So zinc ion will go. So zinc ion acts as a Lewis acid to bind the oxygen and lower and enhance the electrophilicity to the extent that rearrangement doesn't take place. If it goes completely away, if it is protonated, then water is a very good living group. Very good living group, it leaves first. If it is a 3 degree and 2 degree alcohol, then it leaps fast and you get all possible rearranged product. But at low concentration, it has been found that not only you distinguish between three alcohols, but also you can eliminate or restrict the rearranged products from a branched. I'm not talking of 3 degree. 3 degree is not the one which will give you the branched product. Because if it is a 3 degree one, then it will produce a 3 degree carbocation. So there is no room for any promotion. It is a 1 degree or 2 degree having a branch uh, in the adjacent position, then there will be hydride shift or alkyl shift. So that happens. So this 3 degree question doesn't arise. If it is 3 degree, there is no question of any rearrangement. Rearrangement occurs in 1 degree and 2 degree having some branch in the adjacent position. So that will be restricted because of this. It won't completely break down before the nucleophile attacks. Got it? Rudra, got it?
Yes, sir.
Now you have another method of getting alkyl halide is through particularly this is HCl and you can have HBr, HCl, HBr. This HBr can be produced in situ by taking a mixture of KBr with H3PO4. So it produces HBr in calculated quantities, and same thing will happen because this will produce HBr. Similarly, you can get HI. HI can be taken as a mixture of Ki and H3PO4, just like KBr. So it will produce HI and it will produce Ri plus water. But don't forget, if it is acid and if there is enough branch in the adjacent position, it will go for rearrange products. The other method of getting alkyl halide from alcohol is with PCl3, PBr3, PI3. But since PBr5 and PI5 they are unstable, so only PCl5 can be used for alkyl chloride. But for bromide and iodide, you can use PBr3 and PI3. You cannot use PBr5, which is unstable. PI5 is still unstable. So alcohol with PCl5 is the best choice. It is SN2 process. We shall study in detail. There will be inversion of configuration. The OH will go, and this will be Cl, and the other products are POCl3 plus HCl. And you will get dense white fumes. The HCl will appear as a mist. It will go up and sit on moisture to produce white, dense white fumes. And also, you can use PCl3. So in PCl3, it is same SN2, but the products will be, you will need 3 of them to produce 3 RCl plus S3PO3, phosphorus acid. So the OH, 3 OH will be undergoing, substitution, and phosphorus will be bonded to 3 OH group. Of course, then after that it will undergo a little bit of rearrangement, because in phosphorus acid, one hydrogen is directly bonded to phosphorus. So you get RCl. But for bromide, PBr3 is not marketed. You can get PBr3 in situ by combining phosphorus, red phosphorus with bromine. It will produce PBr3, and same thing will happen. There will be 3 RBr plus S3PO3. S3PO3 is the common product. Same thing will happen if you take PI3, which is not available, but you can get this PI3 by combining P4 with iodine. So you get Ri plus S3PO3. So these are, interestingly, another method which is real interest for higher level is use of thionyl chloride, not sulfuryl chloride. Remember this, we'll study the mechanism ROH. If you use thionyl chloride, yes, it is only for chlorine, only for chloride. There is no thionyl bromide. So that will, but the mechanism is SNI, internal. That means it will undergo no inversion, no racemization. It will be exactly retention of configuration. The mechanism will be something different. The side where OH is present, from same side Cl will come in a very typical manner, in a cyclic manner it will come, not use the other side. It will not allow the formation of carbocation, and it will remain in the position of OH, and so there will be retention of configuration. SO2 plus HCl, they will go, and here there is retention of configuration. Just R will remain as R, S will remain as S. Retention of configuration. S and I. So, to conclude, for alkyl chloride, you have so many HCl. Sometimes it is Better to add a little bit of zinc chloride for arresting mm, rearrangement. PCl3, PCl5, and the SNI SOCl2. There are so many choices for getting alkyl chloride from alcohol, but for getting RBR, there is only two: HBr, which is obtained by mixing in situ KBr and H3PO4, and of course Pi3, which is obtained by adding PBr3, which is obtained by adding red phosphorus with bromine. And for iodide, you have also two choices from alcohol. HI is obtained from Ki plus H3PO4, and Pi3, which is obtained by adding phosphorus with iodine. So we will go to other methods, Hunsdiker rearrangement. Hmm. Yeah. The fourth one is the Borodin reaction, Hunsdiker. Sometimes it is called Borodin reaction. So what happens here, you take silver salt, that is must. Silver salt reacts with halogen in presence of carbon tetrachloride, that is the solvent, silver salt of carboxylic acid. So very easily it forms Rx plus CO2 gas goes out and 1X gives a precipitate AgX. So here the reactivity has been studied. The bromination is more reactive than chlorination, and 1 degree alkyl, this alkyl is more reactive than 2 degree alkyl, more reactive than 3 degree alkyl. And the mechanism is a radical mechanism, intermediate mechanism, something very different. Radical mechanism, free radical mechanism, intimate radical pair is formed. Now see, supposing I'll tell you the mechanism is very simple. Once you are talking of radical, you have to go for fish hook arrow. Sorry. So what happens? So this becomes first RCOO dot Br dot, and one Br dot and Ag dot. No plus minus. Ag dot and Br dot will give you AgBr precipitate. So this is an intimate radical pair. There is no carbocation, nothing. That has been found in during the mechanism. So this intimate radical pair in the next step, I'm just writing down below it. Next step, it, see what happens. Automatically this lone electron comes here, carbon dioxide goes out. So the Br dot and R dot, they combine to produce RBr or plus CO2. So this goes via a radical pair mechanism that has been established. Then the other fifth method is specific. Over, have you written down?
Yes, sir.
This is preparation of alkyl iodide from alkyl chloride and alkyl bromide. This is called the Finkelstein reaction. This is simple. To get iodide was difficult from alkane, but once you get alkyl chloride or bromide and take NaI in acetone, and this will be SN2, to get Ri plus NaBr. I minus is a very good nucleophile, as you will know. So here 1 degree greater than 2 degree and 3 degree does not give this one. 3 degree halide will undergo elimination easily. So 1 degree is the best choice, followed by 2 degree. 2 degree also, some bias for elimination is there, but 1 degree is the best choice. 2 degree can happen. So supposing I'll say, how will you convert same thing will happen, you just write down below that, same thing will happen with RBr. Because I minus are better, is better nucleophile than chloride and bromide. So a better nucleophile can displace a weaker nucleophile. Although we shall study I minus is a stronger base, is a weaker base, I'm sorry, weaker base, should have been a weaker nucleophile, but here the situation is opposite in the group, the situation is opposite. Basicity and nucleophilicity go in opposite direction due to the softness of the base, I minus. So supposing we have this chloride, we just treat it with NaI in acetone. This is 1 degree, remember. Acetone, SN2 process will occur. So I minus will go and this will attack. But we cannot know, this is 1 degree, the inversion cannot be felt unless otherwise you label it with a deuterium. This carbon is labeled with a deuterium to make it chiral, then only you can visualize and prove that the mechanism is SN2. And for the preparation of, this is 6, of our alkyl fluoride from alkyl chloride and bromide. This is famously called the Schwarz reaction. The Schwarz reaction. So take alkyl chloride or alkyl bromide with silver fluoride or other ionic fluorides. So there will be displacement SN reaction. Since AgF is soluble, but AgCl, AgBr, AgI, they are sparingly soluble. So you get a precipitate. This is Schwarz reaction. Same thing will happen with RBr. You can use many other substitutes. The other reagents which can use to fluorinate is you can use mercurous fluoride, you can use cobalt fluoride, antimony fluoride, you can use mercuric fluoride. All these fluorides they can also be used in place of silver fluoride to substitute chloride and bromide with fluoride. Well, now time has come for very interesting this is properties where we shall be slowly and steadily entering into the SN mechanism. The hallmark of haloalkanes is SN. So we shall be studying in details. SN reactions. In general, SN reactions. There are so many types of SN mechanisms, SN1, SN2, SNI, as I told you. And then all the three will have their corresponding rearrangement, allylic rearrangement, SNI1 dash, SN2 dash, SNI dash. Now, the basic principle for any SN process, a stronger nucleophile in general base can displace a weaker nucleophile. Nucleophiles are bases. So that is the principle. This should be a stronger, this should be weaker. Otherwise, it's not possible. Example, if you take RBr with OH minus, which is a strong base, being the conjugate of a weak acid water, is a very strong base, as nucleophile, then this reaction is feasible. Doesn't matter whether it is SN1 or SN2, that depends on R. I'm not entering in deep into the mechanism, but saying the fundamental principle. This is a weaker base. This is a stronger base. Stronger bases are stronger nucleophiles in general. But the opposite reaction is not possible. Supposing you take alcohol, treat it with I minus from Ki. Had it been Hi, then it will protonate and the leaving group is not OH minus. It is water, which is a weak base, good leaving group. So that is happening. So from Ki, if you write down of your own, then it will be say Ri plus OH minus or KOH. Such a reaction is not feasible. because this is a strong base and hence a strong nucleophile. This is a weak base. But what happens during the addition of HI? That happens, we have seen, because in the mechanism, the first step is the protonation. To give you protonated water. Now, the SN mechanism starts from here, not alcohol, but protonated alcohol is the real substrate to undertake SN1 or SN2, depending on the nature of R. So here you have I minus, supposing it will this is a weak base and I minus is a stronger nucleophile. This is a weaker nucleophile. But because and water, you just know, is a good living group. And that is why the slogan, a stronger base can displace a weaker base. Because weaker bases are good living groups. They will go. Stronger bases are good attacking groups. They will attack and they will stick into the carbon, onto the carbon, and expel out the weaker base as a living group. Now see, another example I'm giving you. You will tell the possibility. Say you are taking Grignard reagent, RMGX, plus you are taking an alkyne having acidic hydrogen atom. So supposing you write down, this is, R minus as a nucleophile will attack here and this will go. So you get an alkane. We have studied in the preparation of alkane from Grignard reagent, and there will be C minus and MgBrX. This will be remaining as an intimate ion pair. That's okay. But is it feasible? The answer is yes, because R minus is a stronger base, being the conjugate of the weak acid RH alkane. But here the alkyne ion is a weaker base. I mean, comparatively, this is stronger, this is less stronger comparatively, because it is the conjugate of alkyne. Alkyne has a pKa of 28. This is 40 something. So since alkynes are stronger acids than alkenes, alkynide ions are weaker bases than alkyl carbanions. So this is feasible, but the other way is not feasible. The reverse reaction is not feasible. So with this much of introduction, we will be entering first into all the 15 different SN reactions of alkyl halides. Then we shall study the mechanism in details. One by one we will be going. The first one with OH minus, a strong base, that with the help of KOH or NaOH. Strong base. And we can write down this is formation of alcohols. And the order, reactivity order, is 1 degree greater than 2 degree and 3 degree, just like I told you before. is very, very poor. It will be more susceptible for elimination rather than substitution, because strong base can abstract a proton from the beta position more efficiently than act as a nucleophile to displace the existing group. 1 degree is the best choice. 2 degree, the major product will be no doubt, you'll find elimination. We'll be making a extensive distinction between elimination and substitution, which you'll be using in the advanced stage. But for now, we'll study all the 15 types of nucleophilic displacement reaction. So bear in mind, then for any strong base, 1 degree is the first and foremost choice for substitution, and that too SN2. 2 degree mixed up. Still, elimination ka palla bhari, but there will be appreciable substitution product. 3 degree का कोई नाम और निशान मिट जाएगा, वो elimination will be the exclusive product. तो इसीलिए I am taking deliberately 1 degree halide, and I am taking KOH. Usually, I told you in the NCERT book, you will find aqueous KOH means it is substitution. Alcoholic KOH means it is elimination. So this is a misnomer. Only aqueous KOH will not, mix with the organic compound. Organic compounds are sparingly soluble in water because of the hydrophobicity of R group. So you need to have some alcohol in every reaction using polar solvent. Alcohol is a must. A varied combination of alcohol and water are used. So what NCERT says to young students like you, that if you are taking aqueous KOH, then it is substitution. If it is alcoholic KOH, it is elimination. Of course, I don't say that for 3 degree 3 degree halide, if you are taking aqueous KOH, the NCERT book is anywhere writing, it will be giving you tertiary butyl alcohol. I don't say that. It is writing specifically for ethyl chloride or ethyl bromide. If you add aqueous KOH, you will get ethyl alcohol. But if you take alcoholic KOH, you will get ethylene. That is not correct. Alcohol always is inevitable for any organic reaction. But to my mind, if it is OH minus ion, whether there is more of water or more of alcohol, the major product will be always substitution. Only by taking alcoholic KOH you get alkene, ethylene predominantly. No, it's not possible at all. But you have to follow the NCERT book for the purpose for getting a mark. So aqueous I am writing, but it can be alcoholic or a mixture of both, so that here SN2 mechanism will operate. In one step process, OH minus will come here from the back side and this will go. So you get alcohol, 1 degree alcohol and KX. So this is OH minus is the real nucleophile is OH minus, and the real leaving group is the X minus. But if it is solvolysis, not strong base, solvolysis, like hydrolysis or alcoholysis, simply let us take hydrolysis with water. Same formation of alcohol, like the first point, but the mechanism is different. 3 degree is greater than 2 degree, greater than 1 degree halide. And the mechanism will be SN1. Why? Because 3 degree carbocations are highly stable. For example, I am taking tertiary butyl halide, chloride, bromide, or iodide, and adding water, simply water. So by SN1 mechanism, it will produce tertiary butyl alcohol. And the best suitable is 3 degree. 1 degree is lowest. Because water is not a good nucleophile. So attacking power is very less. So it will be very, very slow. Although elimination will not be possible, but substitution will be slow. The solvolysis will be slow. Now what happens here, because water is a very polar solvent, that facilitates the heterolytic cleavage of this bond. In the rate determining step, carbocation is formed. That is why it is SN1, order is 1. Water acts as a polar solvent to facilitate the heterolytic cleavage. That is why it is SN1. This is slow step. But in the next step, which is fast, that water attacks as a nucleophile. Maybe a strong base, but since carbocations are very reactive, it will find water which is present in large excess. And we know this is pseudo first order reaction because one of the reactants, water, is taken in large excess. So it will produce first protonated alcohol because, and then the next step, deprotonation is inevitable to give you a neutral alcohol. You got it?
Yes, sir.
So here 3 degree is the most reactive. The third one that we'll be doing is with moist silver oxide. This is again formation of alcohol. Because silver oxide will slowly produce hydroxide ion in a very calculated manner. So this OH minus ion is the real nucleophile from here. It will form alcohol. So here 1 degree is greater than 2 degree, 3 degree, just like aqueous KOH or NaOH, say type of. But here you'll get a slower reaction but better yield because silver halide will be precipitate. I am showing you Rx for silver oxide plus water, moist silver oxide. I am writing not AgOH but writing moist silver oxide will give you ROH plus 2 AgX precipitate. This here will be also 2. Here also will be 2. Got it?
Yes, sir.
So silver oxide, moist silver oxide is a very good choice for getting alcohol. Instead of using aqueous KOH, NaOH, you can get this but it is a quantitative reaction, where one of the products will be precipitated out, driving the equilibrium to the right, but it is costly. Silver oxide is really costlier there than potassium hydroxide. And now comes the most important with alkoxide ion, strong base. Using sodium alkoxide or potassium alkoxide. This is what we call Williamson synthesis of ether. Now, once you find it is a strong base, alkoxide ions are the conjugates of alcohols, which are weak acids. So, strong base means even it is stronger accepting methoxide, all alkoxide ions are slightly stronger than hydroxide, because water is a stronger acid than all alcohols excepting methanol. Therefore, OH minus ion is slightly weaker base than alkoxide ions. But all of them are strong bases, being the conjugates of weak acids, alcohol and water. So once it is strong base, the reactivity order is 1 degree greater than 2 degree, and 3 degree is very, very poor. It will not give you the substitution product. So the mechanism will be driven by SN2 in one-step process, attacking from the rear side. So if you take Rx, and I'm deliberately taking RCS2X to show that it is, and take sodium alkoxide, and this is the real nucleophile, which will go in SN2 mechanism in one step, and you get RCS2OR dash. Ether. This is called the Williamson synthesis of ether, and the ionic equation will be like this. The X minus is the leaving group, this is the nucleophile, and this is the leaving group, and the details of which we will be doing in the mechanism, SN1, SN2 and all that. So guys who are watching, because these videos, although are making for the students who are joining here like Rudra, but I thought that why should I not make it public? At least a few guys can watch and see what difference is there here as we go unravel the mystery of haloalkanes and haloarenes more and more, with a lot of examples and problems which are in agreement with the advanced IIT advanced level and other levels like NEET and other levels you will find. Now, I will give you an SAQ here. Supposing let me still make it more simple. Ethyl bromide. I'll give you three things. One is aqueous KOH, was no meaning. Alcoholic KOH I will not give you. The other one is, no, since we are studying ether, I will restrict my discussion to ether. Sodium tertiary butoxide. You have to write down the product. And not this one. I will just have another question. I will be taking tertiary butyl bromide, and I will be giving here sodium ethoxide. Write down the major product in each case. I'm just coming in 1 minute. Yes. Rudra, Kar, Sud, Karhala. Hello and welcome those who are watching from the YouTube, because it will be uploaded just after the class. I will upload it. I used to upload it, but I do not make it public. I make it unlisted, and I share to my students who have missed. But I thought, why not I will make it public? What is the fun? What is the negative factor for which I will not make it public? So I decided to make it public. Because here I am disseminating all my 45 years of experience in coaching IIT aspirants. Of course, the NEET and medical aspirants, they do not have to go to such a deep-rooted understanding and preparation, which the IIT aspirants, they require to get into a good position. Rudra, Hala, got it?
Sir, data elimination.
The first one is a 1-degree halide. I told you 1-degree halide with any strong base, alkoxide ions are strong base, it will go for SN2 mechanism and it will produce an ether. This is the Williamson synthesis that we are studying now. This will produce the ethyl tert-butyl ether. Yes or no? The ethyl tert-butyl ether plus NABR. Forget about NABR. Got it?
Yes, sir.
But since this is a 3-degree halide, you are taking a strong base, whether it is a bulky one or a thin one, doesn't matter. Had it been OH minus also, the same thing would have happened. But according to NCRT or some sorts, that if it is aqueous, then it will go for substitution. No. Yes, yeah. If it will be aqueous, completely aqueous, first of all, this won't be soluble. Tert butyl bromide will not be soluble in pure water. You have to have some alcohol mixed with it. So it becomes aqueous. But more the percentage of water will go for a heterolytic cleavage of this bond. And once a carbocation is formed, some little substitution will happen. Although elimination still will dominate. Unlike the case when you take acetone here, alcohol here, the 100% product will be, if it will be alcoholic, the 100% product will be elimination, as we shall study here, beta elimination. The same alkoxide ion which was acting as a nucleophile here for SN2, this will act as a base, strong base to abstract a beta proton, and it will carry out E2 elimination. I will talk about the details of E2, E1, E1CB plus, ethoxide ion and H plus will become ethanol, and this Br minus will become the friend of Na plus, sitting, waiting for when friend will come and join. You got it? Got the difference? Whenever you find a 3-degree one and here a strong base, usually the conjugates of weak acids like water, like alcohol, like even alkynide ion, cyanide ion, amide ion, these are all strong bases being the conjugates of weak acids, HCN, ammonia, and alkyne, alkane, all these weak acids and their conjugate bases are strong bases, and they will favor elimination from 3-degree. And in 2-degree also, the major product will be elimination, and there will be a sizable, appreciable substitution product. In 1-degree, the substitution product is almost exclusive. So that is why for strong bases, 1-degree halide is the only choice, is the only good choice. You got it?
Yes, sir.
So we have 15. And this is the 5th one, or which one?
So fifth one.
Alcoholysis. Again solvolysis, that time hydrolysis, this time alcoholysis. Preparation of ether. Same, not Williamson synthesis. Here, 3-degree will be greater than 2 degrees, greater than 1 degree. It will be extremely slow 1 degree because the mechanism will be SN1. Just like hydrolysis, you take, say, a 3-degree halide and simply add, instead of supposing you add any alcohol, not alkoxide ion. Alkoxide ion is a strong base. Alcohol is a weak base. Is a weak base, weak acid as well as weak base. So that will favor, if I write in one go, then it will favor the formation of substitution. And the mechanism is same as hydrolysis. First step, because alcohol is polar, not as much, highly polar, but this polarity will facilitate the heterolytic cleavage and form. This is also a pseudo first order reaction. Carbocation plus I minus will go, leaving group will go first, and then in the first step, the alcohol, just like water, will attack to produce a protonated ether, and there is a third step. And then deprotonation will occur to produce TBU लिखि दूची O ET लिखि दूची ହେଲା ହେଲା
Yes,
अरे
sir.
so whenever you are using a weak base like water, it is hydrolysis, you should choose a 3-degree alcohol, 3-degree halide to get a 100%, almost 100%, not 100, exactly 100%, but major product will be substitution. But if you take a strong base and you are using a 3-degree halide, then the major product, sometimes the only product will be elimination from 3-degree. 2-degree, a mixture. 1-degree, the dominant product is substitution. So we close today's class. Another 10 and then mechanism. Oh, okay, of course, a gota sardava with dry silver oxide. Formation of ether. Just like moist silver oxide was forming alcohol, if you take dry, no water, then just like your Urdh reaction, just like your Urdh reaction, so 2 moles of alkyl halide will react with 1 mole of silver oxide to give you ether, symmetrical ether, and 2 AgX. So this is another way to get ether. So we close today's session. The 7th one will start on Saturday. And of course, we will be sitting on Sunday. Bye-bye. I think others, they perhaps chose not to attend. Doesn't matter. They can watch in the video. But we are determined as we continue with our class 12 organic. Our sessions will be more and more interrelated and intense, mechanistically oriented, and we will be take up problems of IIT advanced most often, and therefore will not mind. Bye bye. Those who are watching can think of subscribing to my channel. If you like it, can hit the like button. Bye bye.
Pranam, sir.